Hi, folks. Welcome. My name is Chelsea Troy. I lead the machine learning operations team at Mozilla, and I teach in the master's program in computer science at the University of Chicago. I'm here today with Simon Peyton Jones. Simon Peyton Jones is a Royal Society member and a former computer science professor at the university level, now works with computing at schools, designing programming education for children in the UK, maintains the Haskell programming language, and works as a computing fellow at Epic Games. Welcome, and thank you for joining us, Simon.
Right, nice to see you.
Yeah, it's good to see you too. I'm excited to talk with you about not only computing, but also specifically computing education, because I think that this is an area in which I'd categorize myself as a wonk, and it's not a thing that people talk about as much. People don't want to talk about it as much as I want to talk about it. And so I'm selfishly very excited to talk with you about this topic. So I was wondering, actually, if we could start with an anecdote that you spoke about earlier this year in a talk that you gave at the Darwin College lecture series called Bits with Soul. So for folks who are interested, you can find this talk on YouTube, and it is absolutely fantastic. But the way that it opens, Simon, you talk about an exercise that a teacher gave you like 55 odd years ago, yeah?
Right, yeah, exactly.
Yeah, and the idea is that you work at a bank and you need to be able to very quickly hand this angry man exact sums between 0 and 1,000 every single day. And how do you go about doing that? I'd be curious to hear you talk to folks a little bit about that exercise and what it forced you to do.
Well, this was indeed a problem given to me by my math teacher. So he said, well, as you're the bank clerk and you have this angry customer who comes, and you make a plan that would you put into 10 envelopes particular sums of money. And then when the customer comes and says, I want £763, you go flick, 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 and that's £763. And the question is, what's in the envelopes? So this Bits with Soul talk was specifically to a very general audience. It was everything from 11-year-olds through to social workers and through to professors of quantum mechanics. So it was quite a broad audience. And we'll put a link in the show notes. But this was an important moment for me because I realized after a bit, well, you've got to have an envelope with £1 in it in case he asks for £1, and then he might ask for £2, and so you could have another envelope with £1. But why not have an envelope with £2? Because now with the 2 and the 1, we can make 3. Mm-hmm. And then he might ask for £4. So let's have an envelope with £4. And now we can do £5 by the 4 and the 1, the £6 with the 4 and the 2, £7, the 4 and the 2 and the 1. And then we need one with £8. And before you know it, you have invented the binary number system. So what I thought was so clever, retrospectively, is that my math teacher had forced me to invent the binary number system because he told me a problem which could only really be solved nicely by doing that.
Right.
And so rather than being some sort of abstract thing, let me teach you about base 2 arithmetic, it was a real problem. And so it had this visceral sense of discovery, this kind of aha moment, which I can remember, 55 years later.
Yeah. That's fantastic. When I heard you describe this problem, I thought to myself, oh, this sounds really interesting. I want to give this to my students because I teach a class during the spring called Topics in Software Making an Impact. And this is a class where students learn not just about how to write code, but about the impact of their decisions, about decision making in software engineering as well.
Yeah.
In talking to students, particularly independent students and a couple of students attending office hours in this class, I presented this problem to them. And the thing that students very frequently did, I mean, I didn't know it was going to happen. I wanted to see what was going to happen with students. I was curious whether they would invent the binary number system. Granted, I think they had less time to think about this maybe, but a lot of times what students would do is they would say, okay, well, clearly what I need is 10 envelopes, each with £1 in them, and then 10 envelopes each with £10 in them, and then 10 envelopes with 100. And then I have my 1,000. I'm like, yes, but this is 30 envelopes. I have not figured out yet good cues to figure out how to drive students from that conclusion towards the binary conclusion. I'm curious if you have thoughts on that.
So one thing is to say, you only have 10 envelopes.
Mm-hmm. That's
right.
True.
So that gives them a sort of challenge to say, okay, so it can be done with 10. That's already a clue. Right. Mm-hmm. If you have no idea how many it takes. So my math teacher did this for me. He said, you only have 10 envelopes.
Mm-hmm.
Because otherwise you could have 1,000 envelopes. So, and I suppose another helpful clue is to, it rather drives students directly towards the answer. Supposing he asked for £1.
Mm-hmm.
right? Now, supposing you ask for 2, then your one envelope isn't going to be enough. What would you do? So sort of work up from the ground. That's a very common pattern in computer science, actually, to say, let's try it for 1, let's try it for 2, let's sort of spot the common pattern. Then you get sort of a proof by induction going on, kind of.
Mm-hmm. Yep.
So rather than trying to solve the general problem, trying to solve multiple instances of a small problem, of a small concrete problem, is often a good way to go when you're trying to do problem solving, isn't it? The general problem is too complicated.
Yep, absolutely. This is a thing that has always been extremely important in education, but I have found to be especially important now because with students being able to use large language models to effectively get the answer to the programming problems that I give them in homework, the focus has to shift away from getting the answer and on to the process that I would like them to use in order to find the answer. And that's a process that's going to work regardless of the complexity of the problem. The same processes used iteratively will help them reach answers to more complex problems.
Yeah. I think the whole, LLM thing is a challenge for education because you can, as it were, jump to the answer. But it's a challenge in a little bit of the same way that calculators have been a challenge for the teaching of maths education for a long time, right? So there's a lot of data that suggests that basic numeracy is an important life skill, calculators or not. If you're innumerate, you are sort of somehow handicapped, even though a $5 calculator will do everything you need to do much faster than you could do it and much more flawlessly. So there's something around there that's a bit hard to articulate about, and why is it? So I believe, for example, that we still need to teach children to learn how to program, right? To learn the fundamentals of computer science, right? And including how to program, even if for the programs that they write in this, an LLM could just do it in a flash, just like a calculator could do 9 times 7 in a flash. And yet we spend a lot of time teaching primary school children to do that. For reasons that turn out to be educationally quite sound, sort of counterintuitive that might be. So I think we have to do a bit of work as computer scientists to try to distill what is it that we are trying to actually convey, right, in this process. It's clearly not the ability to write a sorting algorithm anymore, right?
Right.
It's something about problem solving or problem decomposition, but it's a bit, the more you try to get it, the more abstract it becomes. And then I say, go back to concrete problems.
Right. Yep. Yes, I think, it's interesting to see the way that the advent of large language models makes it so easy for students to be able to ask, for example, for insertion sort or something, and then just have insertion sort rather than having to go through the process of understanding the problem solving element in order to get to insertion sort. I think a cancelable take that I have about this is that for a long time before the advent of LLM, students largely weren't doing this anyway. What they were doing was they were looking up an implementation of insertion sort and then memorizing it for the purpose of writing their exam. And a focus on the solving of the problem sort of requires either working, I think, on a less precedented problem, or maybe, like you said, something a little more concrete. There's something very specific about the bank and the angry man and the envelopes that makes this an enticing problem for solving, as opposed to, like, if you were to just say, I don't know how you would do this, but if you told students you need to invent the binary system on this exam, the focus would feel much more like it were the answer. Whereas with the story that you attach to it, there's much more interest value in the problem solving portion. Yeah.
So I've seen this in my son when he was writing Scratch programs. He wanted to play games, right? And he wanted the spaceship to go towards the planet. So he said, "Oh well, and the closer to the planet they get, I want it to start going slower." So he started saying, so I've got to take the distance between the spaceship and the planet and affect that, how much the spaceship moves in each time step. And then, of course, if the spaceship's on the other side of the planet, he was begging for negative numbers.
Right.
He was literally begging for you mean we can have negative numbers? Oh, yes, those are okay. It's like they're not forbidden. So rather than negative numbers being a weird thing you have to learn in maths class, it was a thing that made his spaceship move in the right direction. And if it was not just a one-dimensional thing, right, moving east-west, if the spaceship was moving a bit east-west and a bit north-south, right, it wasn't long before he was doing vector arithmetic, in effect, by saying, I've got to move it this fast in the x direction, this fast in the y direction. And nobody told him that he was doing vector arithmetic, but that was what he sort of instinctively was doing. So again, it was driven by a very concrete problem. But then once you stand back a bit and say, what are we doing here? We're doing these little vectors, and it's not long before the problem becomes a bit too complicated to do intuitively, which is what he was doing. And then you need a bit more underpinning of mathematics. But that, for me, is a great way to learn maths and computer science, is through the driver of concrete motivated contexts.
Right. Yeah. Yeah. I would agree with that. I'd be curious to hear if you'd be willing to share a little bit more about how you went from being that student inventing unwittingly binary mathematics because a teacher asked you to somebody who was working in computer science education yourself. How did you decide to go into that? What brought you into that field?
Oh, well, I mean, it's a bit of a long journey. I'm really a research computer scientist. That's my game, right? So I left university. I joined a company for 2 or 3 years and discovered that working for customers is jolly hard work. So I ended up back at university as an academic, as a lecturer at University College in Glasgow. Then I joined Microsoft Research. So all this time, I'm essentially a professor of computer science. But then I had children. Right. And my children went to school. And in the mid-2000s, we were sitting around the dining room table and I was saying, what are you doing at school? And they were telling me about ICT. And they regarded ICT, information communication technology, that was a school subject in Britain at the time. And they regarded it with kind of dismay and even contempt. And I thought, this is bad, right? But this is a subject that I think is so interesting that I've devoted my entire professional life to it, and which they regard as being dry, boring, and undemanding, right? So what's going on? Because that's not true in natural science, right? If they were, they were also learning about, tadpoles at primary school, right? And that, as a biologist, I would recognize as being part of my discipline, whereas I couldn't really recognize what they were doing as part of the things that I thought were so interesting. So that was when we started this organization, Computing at School, that was a sort of guerrilla group of people who just thought that what we were doing about computing education in Britain, in England in particular, was not really meeting the need. It was not really meeting the need. So, but in that case, rather than just bleating about it, we've got to say what we want. So we ended up deciding, this was, by the way, none of us were working as educationalists. Well, some were school teachers. Quite a lot were simply interested people working in industry, in my case, or in university computer science departments. Then we thought, what's missing is that for natural science and for mathematics, we teach every child those subject disciplines as a foundational discipline. Right. But at the moment, ICT was very much regarded as a vocational or instrumental discipline that you learn because it teaches you useful skills about sleek technology. Right. So we ended up saying we should just reimagine computing not as a subject that's mainly instrumental and vocational, but rather than is mainly foundational, like mathematics, like physics, like chemistry and biology, that every child learns not because they're going to become a professional mathematician or professional biologist, though some will, right? But because they need to have some understanding of the basics of the world that surrounds them in order to have agency over it, to be well-informed citizens, to make well-judged choices about the world that surrounds them. So, and maybe the same is true of computing, that if you want to be an empowered citizen with agency in the digital world, you need to know something about the technology, something about how this technology works, the computer science underneath, right? At an elementary level, right? We teach biology at a pretty elementary level to primary school children, appropriate to them. And then again, we should teach computer science as a pretty elementary level. But at the time, it was pretty radical to say in the mid-2000s, every primary school child should learn computer science in the same way that they do natural science. That was like wild. But to my complete astonishment, it became part of the national curriculum in England. And
That's incredible.
It still says that. Delivering that in reality on the ground in every classroom in the land is still a huge challenge, right? Because it's, teachers need training. There aren't enough resources to do it. And we need a very active vision. But the vision is there. It's really good.
I can imagine. I also am curious to hear what computing education at an elementary school level looks like. My experience of computing education as a child was similar, it sounds like, to your students. I took this class called Computer Applications, and the vast majority of computer applications was the teacher sitting in the corner and reading a book while we logged into these Windows 95 computers, and we spent 40 minutes on the Mavis Beacon typing speed program.
Right.
That's mostly what we did. And I'm curious to hear, were I a child who got to benefit from this computing at school education now, what kinds of things would I be learning about?
Oh, well, so I put a link in the chat. We can put in the show notes. The Barefoot resources. This is specifically aimed at primary school children. What would I expect primary school children to be doing? I like them doing things rather than reading books. I quite would like them to learn to touch type, actually, just because it is so helpful in future life, but not to be the main substance of their course. I'd love them to be programming little robot-y things that physically move around the world. You know, the advent of the BBC Microbit and the Raspberry Pi computer and Arduinos and Crumbles and so forth. There's a lot of work on physical computing in classrooms that mean that primary school children can make things that actually do something and that do much more because you can program them in a very elementary way. I'd love to see, I think, writing little programs. Scratch is very dominant in school as a programming language. And my son absolutely loves it because he can do things that he can't do any other way. He can bring into being stuff that has never existed before and share it with other people. What else? So, of course, alongside all this activity, one thing about computing is it's very easy to get children engaged, right? Staring at screens. We also want to make sure that they're learning something. So I think we need to, articulate what we want them to be learning. So the National Centre for Computing Education is something, again, that we launched in this country in 2018, has built a lot of teaching resources aimed at teachers of children from 6 through to 16, which is meant to be saying, behind all this stuff that you're doing with them, here's what they're supposed to be learning and how the sort of cognitive stuff fits together.
Sure. Yeah. If I could, I'd love to change tack for just a minute and relate this a little bit to the work that you do in maintaining Haskell. One of the things that I talk to my students about is the different sort of skills that they might be employing when they do different sorts of programming. I think a lot of programming education, at least a lot of the education that my students have had by the time they get to me, I teach master's students. So these are 25, 30 years old students. They've taken programming classes and they are chiefly focused on end user applications. They imagine that they're going to go into the world and they're going to make iOS apps or they're going to make web applications or now they want to write large language models, or usually what they're describing is the application surrounding large language models. And compiler design isn't something that I found that they've thought about as much. And some of the things that they would need to optimize for in compiler design are things that are totally foreign to them. I'm curious how you would describe what's magical and interesting to you about this type of computing.
Well, I suppose when I was at university and learning, C and BCPL and Fortran and so forth, now quite a long time ago, I also got introduced to functional programming. So functional programming is programming without side effects. Most programming languages, you say do this and then do this and then do this in sequence, and in which your primary method of computation is mutating variables, right? The variables contain values. The value in the variable changes over time. In functional programming, in contrast, you program with values, not with boxes containing values, and you write functions over that value. So the nearest thing that everybody's come across is Excel. An Excel formula doesn't say do this and then do that. It just says the value of this cell is the sum of these other two cells. That's a very different way about going about programming. And it looks, when I first came across it, I thought, oh, that can't be very interesting, right? You could just build business models or something in that with spreadsheets. But it turned out what I learned from my lecturer there at Cambridge was that, in fact, in functional programming, you could do literally anything. It's a Turing complete language. And in fact, you can do it in some ways a lot better. So functional programming is like a radical and elegant attack on the whole enterprise of programming. Lets you write programs quite different. So I was very attracted by that because it felt like, oh, when you're 21, something that's radical and elegant seems quite exciting. And so then I fell in love with lazy functional programming. And then I became part of a research community that was developing lazy functional programming and ultimately to define this programming language, Haskell. So all of the time, I'm getting back to your question. All of the time, I was it was a bit like the bank clerk with the letters. I was inspired by this aha moment of thinking, wow, if you just take this one idea of purely functional programming with values, and push it really far, you can get a long way, and it looks very different to the mainstream. And then we see, because the nice thing about being an academic is you can afford to push something really far and see if it's better. You don't have to know that it's going to be better. Well, so that's functional programming. And one of the things so then if I was going to build an implementation of Haskell, I had to start building compilers. And it turns out, of course, that functional programming languages are quite good for building compilers. So, of course, Haskell's compiler is written in Haskell, but because compilers in a way are like functions, they take the input program, which is a syntax tree, and they transform it successively into an output program, a sequence of machine instructions you can feed to your x86 machine. And at each stage, you've got so you're not mutating the original source tree, you're just transforming thing from one thing to another. So compilers are quite a good fit with that programming paradigm. Mm-hmm. Yes, and in fact, for a long time, Haskell didn't really have much by way of input-output. Certainly not on GUIs or anything like that. That took a while to develop. That was quite an interesting story in its own right.
Yeah, I would love to hear that story sometime. I don't know that we have time in the next 5 minutes, but sometime I would love to hear it. Sounds good. I do have one more question for you, and it is about your work as a computing fellow at Epic Games. Is that right?
Mm-hmm. Yeah.
Now, as a computing fellow, this is a title, a sort of role that I think my students, for example, as people who are about to enter the field of computer science, are less familiar with. They've heard of software engineers, engineering managers, product managers, designers, these kinds of things. But computing fellow, I don't know if they would consider that as a potential career path or career target. I'm curious if you could talk a little bit about what it means to be a computing fellow at Epic Games.
Oh, it's a kind of strange one-off kind of thing, really. It's because I was age 63 and looking for a job, and it turned out that Epic was in the midst of designing a programming language called Verse. An old friend and drinking companion of mine called Leonard Augustin was already working for Epic on Verse with Tim Sweeney. Now, the reason that Epic is designing this programming language is because the founder and chief executive of Epic, Tim Sweeney, is fundamentally a computer scientist. He's the guy who first implemented the Unreal Engine, and he has been designing Verse in his head for the last couple of decades or so. So my job is, as it were, sort of unemployed computer science professor, which is pretty much what it amounts to at the time, is then he said, so we agreed to work together. So my job is to sort of reverse engineer Verse out of Tim's head and to try to write it down in a way that, everybody else can understand. Tim is he's a remarkable person. He has a very, very strong technical intuition. So he can sort of jump immediately to the answer, but it takes a long time for me and him and Leonard and the others to find out just why is he so convinced that is the point in the design space we want to be at. He sort of leapt there in one go with this sort of amazing technical intuition. It's not the only point you could go to, but it always turns out to be an interesting one.
Okay.
So I wouldn't say that it's a career path. It's more like I feel incredibly fortunate that in my life, people have been willing to pay me to study things that have been very interesting to me, like functional programming and indeed computing education. And then I've happened to land up in somewhat of a one-off situation at Epic.
Sure,
it's quite unusual to be. I don't think many people have a 2-hour conversation with the chief executive every week of a chief executive of a multi-billion-dollar company in which the conversation goes like this. I say, Tim, this is all getting very complicated. And Tim says, Simon, it's all fine. It's all pretty simple. You've just got to think about the denotational semantics.
Yes, of course. The denotational semantics. How could we forget about the denotational
Exactly.
semantics?
Well, not many CEOs have that as their priority, right?
It's true.
Mostly they say, we've got to think about our profitability or our customers or our IPO. But no, it's denotational semantics. I love it. I love it. It's great.
Oh, it sounds lovely. Well, thank you so much for taking this time today, Simon. We really appreciate it. I'm sure that folks are really going to enjoy this. And thanks again for making the time. Really appreciate it.
No, it's been a lot of fun. And I put a blog post that I wrote a couple of years ago about why we should still teach our children to code, even in the age of AI, because I think it is important.
Amazing. Thank you.
Because I think as computer scientists, this is a question we're going to get asked a lot.
Oh, absolutely.
So
yes.
I just thought it might be worth adding to the show notes because people listening to this may get asked this question too. Right. Yep. And what we don't want to do is to wave our arms in the air and say, well, maybe we don't need to teach them to. I think we do. I think they need to understand the fundamentals of computing. And like we need to teach numeracy, I think we need to teach elementary programming, a sense of agency over computers.
Yep, absolutely. While we're on that, let me go ahead and add one to the message chat as well. This is a blog post that I wrote about the way that I do Gen AI policy in my computer science class right now. And I am not claiming to have all of the answers, but we'll be curious to hear if I get feedback from readers about it.
Oh, great. Thank you, Chelsea. I'll read it. Yeah. Good to talk to you.
Good to talk to you too. Thanks, Simon.